SSA 2020 Eastern Section, Abstract 59, Analysis of Microseismicity during Hydraulic Fracture, Application of Spatial Temporal Magnitude Calibration. My name is Raymond Ng with the University of Oklahoma, and my advisor is Dr. Xiaowei Chen, also from the University of Oklahoma. Our motivation for our study is to expand our knowledge in the relationship between injection volume and event size. We test three hypotheses. The first one is to follow the McGar 2014, where the maximum moment is the product of total injected volume and shear modulus. Also, McGar and Barber 2017, total seismic moment scales with injection volume. Following Van der Esk et al. 2016, where the question is posed of whether the largest observed magnitudes are consistent with the sampling statistics of the Gutenberg-Richter magnitude frequency distribution, giving the total number of induced earthquakes at each site. Following Shapiro 2010, we examine how the seismogenic index will respond in adjustment in microseismic magnitude, if at all. However, we believe the treatment fluid types do not play a significant role in the seismogenic index, even though treatment fluid types were applied in different boreholes. The location of the dataset is in East Texas. It is coming from the Cotton Valley Formation in Carthage, Texas, is shown in the black box in Figure A. In Figure B, we see that we are in East Texas in the red box, and the target formation of the Cotton Valley Reservoir is a interbedded sand and shale layers with tight gas. And the dataset we are using is from Rutledge et al. 2004, and this contains 4 hydraulic fracturing treatments, 2 gel fractures, and 2 water fracture treatments. These are shown, the individual treatments are shown in different colors on the figure to the right, where treatments B, A, E, and C, where treatments B and A are gels, and E and C are water treatments. And we have our hydraulic fracturing fluid injection rate. For treatment B and A, we have fairly similar injection rates. However, for treatments E, we have a lower injection rate, and treatment C, we have a higher injection rate comparatively. In the cross-correlation cluster analysis, we apply a minimum cross-correlation coefficient threshold of 0.7. In the upper 2 figures, we have final clusterings for treatment A and B recorded. Each color represents individual clusters based on average cross-correlation from at least 5 geophones. Both treatments are separated into small clusters that are closely spaced in map view. These clusters exhibit time-dependent activation behavior. However, some clusters remain activated throughout the treatment. In the bottom 2 figures, final clustering treatments for E and C, both of which are water fractures. Each color represents each individual cluster based on average cross-correlation from 5 geophones as well. These 2 treatments are dominated by one major cluster, which are shown in red. The largest cluster in treatment E exhibits an anomalous trend. In magnitude calibration, we use principal components analysis, which is performed by using highly similar waveform and calculated by taking the ratio of the largest eigenvalues of the covariance matrix between the 2 waveforms, as shown with events 1 and 2. We set a minimum recorded station threshold for each cluster event to 5 receivers. Only cluster events with a cross-correlation coefficient of value greater than 0.7 are used in the amplitude ratio. Amplitude ratios are used to invert for new magnitude m, where the superscript is referring to the event number, and the logarithmic amplitude AR subscript j and k between templates J and K is the average principal component, maximum diagonal eigenvalue of the covariance of waveforms J and K at each station. The sum of the magnitudes, sum of log 10 m, where n is the total number of waveform events, is inferred from the initial catalog magnitude assigned to each waveform event. Significant improvement in magnitude difference in relation to the log amplitude ratio is shown post-magnitude correction through principal component analysis. We can see higher density of binning of the amplitude ratios and magnitude differences is shown by the heat maps labeled as A and B, where the image resolution is determined by the total number of event pairs within the starting catalog. So in our seismogenic index evaluation, we do see an observed decrease in seismogenic index for treatments A and C, and we observed an increase in seismogenic seismogenic index for treatments B and E. What this means that in the larger the seismogenic index, the larger the probability of a significant magnitude event. The seismogenic index and B value can be used to predict the number of events within a specific magnitude range. That is what we see here with an increased B value for treatments A and a decreased B value for treatments B, C, and E. And this is where A is prior to magnitude calibration, and A prime is the results after magnitude calibration. And we can see in comparison between the prior and post magnitude calibration that there. So in conclusion, we see no significant difference between water fracking and gel proppants in terms of seismogenic potential. The main cause is in the different seismogenic potential is the activation of pre-existing optimally oriented natural fractures. Two of the treatments that had a smaller seismogenic index after magnitude calibration occurred at a greater depth than the other two, which had a larger seismogenic index but occurred at a more shallow depth. So this gives us some indication that it might be something in the physical sense instead of a chemical sense between water and gel treatment that is influencing our seismogenic index. So a possible existence of aseismic slip can also explain the low seismogenic potential of this hydraulic fracture experiment when compared with compiled dataset of previous studies. Real-time analysis of waveform similarity and source parameter analysis can help identify activation of new fractures and seismic slip along pre-existing fractures. Thank you very much. And we have our references shown here. Thank you.